Hey everyone, it's Pranav, and today we're going to be looking at Burnside's lemma. So Burnside's lemma can be useful when solving combinatorics problems, and I'm going to prove the lemma for completeness, which does require us to go over some group theory first. So you can feel free to skip to the theorem statement and the sample problems towards the end, because you don't really need to understand the proof to apply the lemma. But I would still recommend watching through as we go over the requisite content because we go over some terminology that comes up when you use Burnsides. So to start everything off, we do need to define groups. So a group is a pair of G comma plus, where G is a non-empty set, and plus is a function from G times G to G. So this G times G is referring to the Cartesian product of two sets. So the Cartesian product of G to G simply means that we have some element X in G and another element Y in G, and this maps to some element Z in G. So you can think of normal addition. So we have like 1 plus 1 equals 2. This is the same thing as this. So we can define addition on as like a function from R cross R to R. So this pair of the set and function satisfy three properties, which we will call the group axioms. So that's associativity. For all A, B, and C in G, we have that parentheses A plus B, close parentheses, plus C equals A plus close parentheses B plus C. We have identity, so there exists a unique element 0 in G such that 0 plus A equals A plus 0 equals A for all A in G. And the last one is inverse, so for all A in G, there exists an inverse element negative A such that A plus negative A equals negative A plus A equals 0. So groups are closely related to symmetry, and we often use them to describe the structure of things. On that hand, let's go to symmetry groups. So a symmetry group is a group whose elements are transformations on an object where the object stays invariant. And the operation for a symmetry group is composition, which is usually denoted by this circle. So you may have seen like F circle G of X, and this is function composition. So we apply one function first, then the other. So it's similar here. So for an example, let's look at rotation by n degrees. So we can say that G equals like, let's say 1 degree rotation, 2 degree rotation, so on, all the way to 359 degree rotation, 360 degree rotation, or something. So this is obviously the identity, because it's the same thing as not rotating at all. So we have an identity. And similarly, we can have G have negatives, so like negative 1 degree, negative 2 degrees, so on, all the way to negative 359 degrees. So now we've defined the inverses. So when we compose a 1 degree rotation and a negative 1 degree rotation, we are left with the identity, which is the 0 degree rotation. And since this pretty much works analogously to addition, we can just see that associativity would hold as well. So we do have that this satisfies the group axioms, which were these 3 bullet points here. So now let's look at group actions. So a symmetry group can act on a set of objects, and we can transform those objects by the transformations that are the elements of the group. So for instance, we can rotate a square by 90 degrees, like clockwise, and that makes a diamond shape instead. So like, yeah, we've produced this. So you can describe this formally by defining group actions. So suppose G is a symmetry group with identity E, and suppose that X is a set. So a left group action phi of G on X is a function from G times X to X. So one element from G and one element from X that maps to some other element in X, or the same one, that satisfies the following two properties. So we have identity in phi. So for all X in X, phi of E, where E is the identity of G, and X equals X. So think about this. A rotation by 0 degrees doesn't actually change an object. And composition. So for all G and H in capital G and X in capital X, we have that phi of G composed with H and then X is the same thing, or equals phi of G, comma, phi of H and X. So sometimes we can omit the phi and just write phi of G X as G times X, for notational convenience. So now that we've talked about group actions, we can talk about orbits, stabilizers, and fixed points, which are very important when we are solving problems with Burnside's lemma. So when referring to a symmetry group, we often omit the circle or the composition operation because it's understood to be implied. So we refer to a symmetry group as just the set. So often we'll just call the group G instead of writing out like G plus, or like the symmetry group of graphs on 4 vertices, which we can denote by S4 instead of writing like S4 and composition. So let's define some more relevant terms to group actions. So suppose G is a group acting on a set X. A fixed point of an element G in G is an X in capital X such that phi of G X equals X. So it's basically the transformation isn't actually changing the object. So the stabilizer G sub X of a point X in X is the set of elements G in G such that X is a fixed point of G. So we have that G of X equals G such that phi of Gx equals X. In other words, it's the set of all fixed points. So the orbit of an element X in X is the set of elements Y in X, such that phi of Gx equals Y for some G in G. So the orbit is all the possible objects we can get by applying the transformations in the group G to an object X. So now we can state, but we won't prove, an important theorem which we'll use to prove Burnside's lemma. So this is called the orbit stabilizer theorem. So suppose G is a group acting on a set X. Denote the stabilizer of X in X as G sub X like before, and the orbit of X as O sub X. So if the orbit of X is finite, then the index G colon G sub X is also finite, and we have that the index is equal to the cardinality of the orbit. If G is finite, then we have the cardinality of G sub X times the cardinality of O sub X, so the stabilizer times the orbit, equals the cardinality of G. So in this case, that's the set. So you can ignore the stuff about the index mostly. What we're concerned with is this. So yeah, I'm not going to prove it because it's not insightful for our purposes, and you need to know a little bit more group theory than what I've covered here. So I'm just going to skip that. If you do want to see the proof, I included it in the handout though. So now we can state Burnside's lemma. So suppose G is a finite group acting on the set X. So let X slash G be the set of orbits of X. So all the elements little x in capital X. So for any G in capital G, we define X to the G to be the set of points in X which are fixed by G. So this is the set of fixed points. But instead of the transformations, now it's based on for each transformation what points are fixed by the transformation instead of the other way around, which was the stabilizer. So then we have that the cardinality of X slash G is 1 over the cardinality of the group G times the sum of all G in G, so every rotation or every transformation in G times the cardinality of the set X to the G. So this may seem really complicated, but this is more so a formalization of the intuition that we use to approach certain counting problems. So I think that will become clearer once I actually solve an example problem and show you. But for now, let's move on to proving Burnsides. So we have the sum G in G for X, the cardinality of X to the G, right? So this is what we're concerned with right now. So let's find a way to rewrite this in terms of the objects in X instead of the actions in G. So if we think about it, this should be equal to the set G in G such that phi of G on X equals X, right? We've just swapped the indices here. But we've seen this before. This is just a stabilizer. So this is X and X for the cardinality of G sub X. So now, if we recall the orbit stabilizer theorem, we have that the orbit times the stabilizer equals the cardinality of the entire group set. So this implies, this implies that we have that G of X equals G divided by O sub X. So if we substitute that into the sum, we can pull out the G because it doesn't change as we go through each of the objects in the set X. So you can just rewrite the sum again as G times the sum for X in X of 1 over O sub X. So now let's pause and think of each object X's contribution to the sum in a fixed orbit. So each X contributes 1 over O to the sum. And since there are exactly O of these, the total contributions of the X is just 1. So this is just the number of the orbits. And we know that is just X slash G. So from what we have here, so recall that this is equivalent. So this is equivalent to G times X slash G. But since we've made reversible substitutions to get to this point, this should all be equal to this. So we have that the sum G in G of X to the G equals the cardinality of G times the cardinality of X slash G, and the result follows because we can simply divide by the cardinality of G on both sides, and we get the theorem statement for Burnsides as desired. So we're done. This proof is a pretty good example of how a sum swap can be useful. So we swapped the indices completely, and we were able to simplify the problem down into something that we could tackle and then show that that was equal in what we wanted. So let's actually solve a problem using Burnside. So compute the number of distinct ways Pranav can color a cube by painting each face of the cube, one of 6 distinct given colors. Cubes are considered distinct if they cannot be obtained from each other using rotations. So let's let X be the set of all possible colorings of the cube without rotation. So we have X. So it's all possible rotations, or all possible colorings, sorry. Colorings without rotation. So we can easily see that the cardinality of x is just 6 factorial because we have 6 colors and we can only use each color once on all of the 6 faces. So this is just 720. Next, let's let G be the possible rotations. So this is the symmetric group of rotations on the cube. We can calculate the cardinality of G by noting that we have 6 ways to choose a top face and 4 ways to choose a front face. So we should just have 24 different rotations. At this point, you could just go, oh hey, 720 divided by 24 equals 30, because we can group the possible colorings into each of the 24 rotations, and that should be the answer. And this is correct, but we should go, let's use the formalization of Burnsides to look at this problem. So since we have 6 different colors, the cube outputs a distinct coloring under rotation. So there are no fixed points other than when we don't rotate the cube at all. So in a more formal way, we have that x to the g is the empty set for all g in G except when G equals E, the identity. So that means all we have to consider are the fixed points under the identity transformation and nothing else. So if we think about it, this should just be x, as all the elements are fixed under the identity by the definition of the identity. So that leaves us with x slash g, the orbits, equals 1 over g times the sum from g in G of x to g. And this is just 1 over 24 times 720, and that's 30, like we got up there. So I think this shows that Burnsides actually isn't that complicated, and it's just a more formalization or a formal idea of what we already think and know. So let's move on to another example. So it's also pertains to colorings of cubes. So this is just a typed up version of the solution. So you can pause and read if you don't like the handwritten one. So let's look at example 2, which is more cube colorings. So now that he found out how many ways he could color a cube using 6 colors, Pranav is wondering how many ways he could color a cube with n colors, given that he can use each color more than once and that 2 colorings are considered distinct if one cannot be obtained by a rotation of the other. So, like before, let's let x be the set of all colorings, all possible colorings, without rotation, of course. So this time, x is n to the 6, because we can use each color more than once. That's the only thing that'll be different though, because if we define G as the same as the example 1, we still have that G equals 20. The cardinality of G is 24. But this time, since we can repeat colors and we don't actually know the number of colors, there could be less colors than 6, for example. We do have to consider each of the individual rotations in G, because there are fixed points this time. So let's look at them. So the elements of G are as follows, if we think about it. There's, of course, the identity rotation. And this has n to the 6 fixed points, because all the elements of x are unchanged under identity. There should be 3 180-degree rotations, so 3 180-degree rotations. And these should leave each of which of these leaves n to the 4 of the possible colorings unchanged. Next, there are 6 90-degree face rotations. Each of these leaves n cubed of the elements of x. So half of them unchanged, not half of them, sorry. N cubed of the elements of x unchanged. So there are 6 180-degree edge rotations. And these also leave n cubed of the elements unchanged. And lastly, we have 8 120-degree vertex rotations. These leave n squared elements of x unchanged. So we've calculated the fixed points for each of the elements in G. So by Burnsides, we can find x/g now, the orbit. So we know that it's 1 over 24 times the sum of g and g for x to the g. So all we have to do is add these up. So we have 1 over 24 times, so the identity has n to the 6. Then the 180-degree rotations have n to the 4, and there are 3 of them. So 3n to the 4. Then, noticing that both the face and the edge rotations each have n cubed fixed points, and there are 6 of each, we just add them, so we get 12n cubed plus 8 times n squared for the vertex rotations. So this is our answer. We've obtained a polynomial that will give us the number of rotations, or the number of distinct colorings for n sides. So this is just the typed up solution. It does take 2 slides because we have to list out all the fixed points. So yeah. This last example shows us that Burnside's lemma can be very useful in places where we don't actually expect it. So prove for all integers, positive integers n and k, that n divides the sum from I equals 0 to n minus 1 of k to the GCD of in. So normally we'd use a number theoretic argument to solve this problem, but we can actually construct a combinatorial argument instead. So consider a necklace with n beads that we want to color with k different colors. How many distinct ways can this be accomplished up to rotations? So if we let x be the set of all colorings, colorings, then the cardinality of x is just k to the n. So then we can let G be the group of rotations with order n. So let's consider the rotation by I beads. If there's a rotational symmetry after I turns, then the first bead, so we have bead 1, we have some more beads in between, and we have b of I plus 1, they should be the same color. So the I plus 1 bead must be the same color as the first bead. So we can generalize this and construct it as a regular polygon with n vertices. So connecting every ith vertex will yield an orbit of length n over GCD in. This separates the beads into precisely GCD of IN groups, which each yield K to the GCD IN colorings, distinct colorings. So by Burnside's lemma, the total number of distinct ways would be 1 over n, since there are n beads, I equals 0 to n minus 1, k to the GCD IN. And since the number of distinct ways that we can color a necklace has to be an integer, this implies the result that I equals 0 to n minus 1, k to GCD IN. It implies that n divides the sum as desired. And we're done. So this is just a typed up version of that without the diagrams. So I think, yeah, so that last example was kind of hard, and it was illustrative to how Burnside's lemma is actually useful outside of combinatorics. So there is a generalization of Burnside's lemma, which is called the Polya enumeration theorem. And the example above in particular is quite similar to that. And I'd recommend that if you enjoyed this content and you're interested in learning more about it, that you read about Polya enumeration on a site like Brilliant or Wikipedia. But outside of that, that's everything that we have for this week's lecture. So I hope you found the examples instructive and the content interesting. See you next time.